Good afternoon, everyone. Today is lecture number 16 of this heat treatment class, and these are the today's content. One is tempered microstructure of martensite. Here we'll see the transmission electron micrographs of some steels, which is of tempered martensite, right? And we'll see difference between BCC and BCT unit cell, and soon we'll see special heat treatment on steels. So there are certain special heat treatments which is given to the steels for better properties, and we'll have another heat treatment called sub-zero heat treatment. So these are the today's content. So you can see here, these are the three transmission electron micrographs, basically this one, and this one. So this image is showing you a tempered martensitic microstructure, but it is this steel has undergone a light tempering, right? So this is the light tempered microstructures, lightly tempered martensite, you can say. You can see, you can able to see here is, if you remember, if people remember what is the structure of this martensite. Martensite, if you look in 3 dimension, it is basically either a plate or a lath. Basically we call it as a plate, or basically you can call it as a lath. If you're calling it as a lath, you have to remember that the end portions are thinner, it's kind of sharp ends, and the middle part is somewhat wider in nature, right? So those are laths basically. So here we have martensitic laths, and this region is appearing as a darker region because if you remember, martensite when forms from austenite, there is a shear, there is a plastic deformation happens. So due to which a lot of dislocation density is also there inside the martensitic laths. So due to presence of lot of dislocation density here, this is appearing as a darker region, right? So direction of lath you can see, and you have to remember, see that this is the direction of lath here in this, in this direction, and here it will be like this directions. And you have to remember the martensitic lath or the plate, they formed on certain crystallographic planes. They do not form on random planes on the austenitic grains, right? They form on certain or a specific crystallographic planes basically. So they have a preferred orientation also. These laths have a preferred orientations. They do not form here and there in different orientations. That is also an important point you have to remember about martensite. And and another important point I would like to mention here is, saying martensite are acicular or needle shape, it is actually a wrong statement. It is not the right statement, because many of the books you can see, they have written that martensite looks like a needle, but it is not true exactly. In 3 dimension, it is either plate or it is either a lath shape. Then you can see, then this next micrograph, you can see this micrograph is obtained after more interval of time and at high temperature of tempering. So you understand, as I told, tempering is done below A1 temperature basically, but if the temperature is somewhat higher, then what happens? Recovery is taking place here. You can see recovery. If you remember, recovery stage, what happens basically? Annihilation of dislocations occur. Dislocations start getting disappear. So you can see this microstructure is appearing as a lighter portion, or it is appearing as white nature. This is darker and this is white, or this is darker and this is light one. The light nature is due to disappearance of the dislocation density. You can see the dislocation density is very less right now, but you can able to see the laths easily. You can see this is one lath, this is one lath, this is one lath, this is one lath. Here the direction of lath is here like this. Here the direction of lath is like this. These are the laths, right? And in the third structure, you can see here recrystallization is happening. That means the lath has converted into now ferrite. You can able to see the ferrite grains, and cementites is there, right? This is the final microstructure. That means with increasing in the tempering time and temperature also, you can able to see finally we have cementite and ferrite here. Now this slide is showing you the change in the carbide structure, or what kind of carbides we have, or what kind of precipitate we have. So this structure is showing you lath martensitic structure, right? That means this structure is obtained after hardening heat treatment. Just imagine you are doing hardening heat treatment on steel, and you'll get this kind of microstructure. This is the transmission electron micrograph. You can able to see the lath easily. This is one lath, you can see. This is one lath. 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 But some laths are some lighter and some laths are darker. You understand this is the distribution of these dislocations. Here the dislocation density is very high, so it is appearing as darker. This dislocation density is very high. Here dislocation density is very high. Here also dislocation density is very high, but it is less here. So we can now understand. And you have to remember, this is one of the reason why martensite is very hard and stronger, because of high dislocation density. So these are the one first reason behind the high hardness value or high strength of the martensite is the tetragonality. That means exactly what happens. The carbon get trapped inside the martensite, right? The carbon which is present in the austenite is getting trapped inside the martensites, right? Martensite is a BCT structure, if you remember, body center tetragonal structure, right? So the lattice is getting distorted tetragonally, or this kind of distortion is called tetragonal distortion. So this tetragonal distortion, basically they interact in a strong way with the dislocations. Because if you remember, the strength or hardness increases if the dislocation movement will be hindered or restricted. So if dislocation will strongly interact with this tetragonal distortion, then strength will increase. So which is happening in the martensite. That is one of the reason. And the reason is the high dislocation density also. In the martensite, we have large dislocation numbers, which increases the strength and hardness. But upon tempering, you can see what is happening to the that means if you remember, on tempering the carbon will eject out from the martensitic laths, right? So it reacts with the iron and it will form carbides. Basically initial carbides, you can see the carbides here, very small fine carbides. These are basically intermediate carbides, or you can say that is basically uh, transition carbides, which are very fine. It is very difficult to look into these carbides. These are basically either Fe2C or Fe2.4C. You can call this the Eta carbide, or it is epsilon carbide. Fe2.4C is epsilon carbide, which is HCP structure, hexagonal close-packed structure. But cementite is basically complex orthorhombic structure, right? But after doing tempering for more interval of time at high temperature, you can see this you will get equilibrium carbides. Equilibrium carbides is nothing but your cementite. These are the plates of cementite. You can able to see the plate of cementite is here. Right? So finally, these carbides will convert into plates of cementite. So you can see here martensite, then transition carbides, zeta and epsilon, then finally equilibrium carbides. This is the sequence. Now, difference between BCC and BCT. If you remember, this is a BCC structure, and BCC structure, if you people have remember how to define a unit cell. Unit cell can be defined on the basis of lattice parameter, if you remember. One is the angles between the edge length, that is alpha, beta, and gamma, and the edge lengths A, B, and C, or you can call A1, A2, and A3. So you can able to see the difference between tetragonal, isometric. Isometric is nothing but the BCC. Tetragonal is this one. You can see the difference. The C-axis is higher here, but the C-axis is same as that of this X-axis and Y-axis. So you can see this is A1, this is A2, and this is A3. All are equal, and all angles are 90 degree. But here what is happening? A1 is equal to A2, but it is not equal to C. Right? So A1 is equal to A2 is not equal to C. The C direction is longer. It's called tetragonal. But all angles are 90 degree. So you can see this is FCC structure. The FCC, that means it is the austenite. The austenite will transform into martensite, which is BCT structure. Because at body center, And the carbon atoms are present in the octahedral voids, which is the center of the edge. Again, this is you can call this is a hardening heat treatment, where austenite will convert into martensite, right? So tetragonality is increasing with increasing in the carbon percentage. More is the carbon, more is the C axis, or the length of the C axis will be more. Similarly, upon tempering, this BCT will convert it into BCC, right? Now, okay, now we'll discuss about the two special heat treatments called Martempering and austempering. So first one is the Martempering heat treatment. The name itself is saying Martempering, martensite and tempering. Two things are there. Martensite formation will be there, then we'll do tempering of it, right? So Martempering. So it is a special heat treatment to get martensite, which don't crack in brittle mode, like conventional martensite formed by hardening, right? So if you remember the conventional heat treatment, which is hardening and tempering, right? So if you remember, in case of hardening heat treatment, we get martensite, right? But that martensite is very brittle. It is hard, but it is brittle. It will break easily by brittle mode. And that martensite also contains a lot of residual stresses. And if you understand why the residual stresses is coming, one reason is when martensite forms, there is a volume expansion. 3% volume expansion occurs when martensite forms, basically. So due to volume expansion, and contraction also happens during cooling, during quenching process, so that leads to some residual stresses. And other residual stresses comes due to this there is a steeper gradient is there, steep temperature gradient is there. Why? Because if you understand, if we have a thicker cross section of steel, the surface of the steel, the cooling rate is different, and the core, the cooling rate is different, right? So difference in cooling rate leads to, again, thermal stresses, right? So this, that leads to lot of internal stresses present in the martensite, right? So conventional hardening heat treatment will give you martensite, which is brittle and having residual stresses in it. But Martempering is very good. Martempering will prevent this lot of internal stresses. Some internal stresses will be there, but it will reduce the amount of internal stresses in the martensite. Here it is written, it has been seen that residual stresses pattern in the steel sample is tensile stress at the surface, and in core it is compression stress in fully hardened, and in shallow hardened it is just opposite. So Martempering is a special heat treatment which prevents the generation of residual stresses. That means the residual stresses will be still there, but it is minimized. And also it prevents the cracking of steel during service. This is important about the Martempering. Now we'll see the TTT diagram and the cooling curves. This is the TTT diagram we have, and this is the cooling curves. Here, this is the TTT diagram we have, and this is the cooling curves. And if you remember, this is your equilibrium transformation temperature, AE1, and this is also AE1, equilibrium transformation temperature. So above AE1, austenite is a stable phase. Below AE1, austenite is not stable. It will transform into some other phases, right? So this here, above AE1, austenite is a stable phase. Below AE1, austenite will be not stable. It will transform into some other phases, right? So this is the temperature versus time plot, fine. So you can see this is the cooling curve. This is cooling curve, and this is again cooling curve. So this is this plot is showing you the conventional hardening process and tempering process. So you can see. Can you people tell me why we have these two cooling curves for a same piece of steel? For a same piece of steel, why we have a two cooling curve? We should have only single cooling curve, right? Can you people...
One is for surface and the other is for
Very
inner
good,
part.
very good. It is already written over here, actually. So this is for surface, and this is for center. So why? So which one is which cooling rate is fast? Which cooling rate is slow?
Surface is first.
Yes, surface is fast. How you can say surface is fast?
Because sir, at the surface, direct heat loss is done to the
No,
atmosphere.
that is fine. But from this plot, how you can say surface cooling rate is faster?
So this that curve is more steeper.
Curve is more steeper. Anything else? Yeah, that is steeper one part. Anything else? How many of
Sir,
you have remember what is critical cooling rate?
yes, sir.
Hmm.
So the cooling rate at which just transformation starts.
Okay. Which kind of transformation start? Critical cooling rate is that cooling rate where the cooling curve will just touch the nose of the C curve. That means martensite will form. That means austenite will transform into martensite. Just it will touch. Just. Hmm. So this cooling curve will be what? It is far away from the critical cooling curve, right? It is far away from the nose of the C curve. This cooling curve is far away from the nose of the C curve. But this cooling curve is close to the critical cooling rate, or it is close to the nose of the C curve. So this cooling rate is faster, but this cooling rate is slow. Why is slow? Because you understand center. The center portion is not exposed to the surface. So cooling will be slower, but the surface will be exposed to the atmosphere. The cooling rate will be higher at the surface. That's why we have two cooling curve. But this is for a same piece of steel. Hmm. So this is the conventional heat treatment. You understand the cooling curve is like this. Martensite will form. You can understand this is the MS temperature, Martensite start temperature. This is Martensite finish temperature. So we are quenching the steel from austenitizing region to below MF. So Martensite will form. Then we are doing tempering of this. So this is tempering. You will get tempered Martensite. Right? The conventional heat treatment. But this Martensite will be brittle one, having lot of internal stresses. Right? But what is this Martempering heat treatment? So Martempering heat treatment, what we are doing basically, we are taking the steel to the austenitizing temperature. From austenitizing temperature, we have to hold the steel. Then finally, we have to quench the steel. So how we have to quench the steel? We have to quench the steel to a temperature which is just above the MS temperature, because this is the MS temperature. We have to hold the steel here. So we are quenching the steel to the temperature just above the MS, and we have to hold it some particular interval time we have to hold it. So that what will happen, the entire steel will be at a single temperature now, the surface and the center. This is done by using a salt bath. The salt bath temperature is this much. So entire steel will become the temperature at which the salt bath is there. Finally, what we'll do, we'll then cool it in air at a faster rate. That this is called air cooling. And finally we'll get martensite. But this martensite which is obtained is having minimum residual stresses. It will not easily break by this brittle mode, but this steel will again give tempering heat treatment somewhat. So this is tempering, and you'll get a tempered martensite. So this is called Martempering heat treatment. So you can easily write why two cooling curves for a single sample in this plot. You can write it. And second one is difference between conventional route and Martempering. You can easily write it. What is the difference? Can you people figure it out? What is the difference between these two? Martempering heat treatment and this is conventional heat treatment, hardening and tempering. What is the difference? First difference. Can you people tell me the first difference? What is the difference between this cooling, this curve and this curve? This plot and this plot? It is clearly visible. Just look at the cooling curve and you can easily answer.
Sir, in Martempering, there is an additional holding time before martensite start temperature.
Okay, fine. But you can, okay, that is right. But you can say like this, in this conventional heat treatment, hardening and tempering, in case of hardening, we are quenching the steel from austenitizing region directly to below MF, right? It is a continuous cooling. You are doing continuous cooling from austenitizing temperature below MF. This is the MF temperature, martensite finish temperature, right? And we are getting martensite. But in this case, we are not doing that like that exactly. What we are doing, we are quenching the steel from the austenitizing region to a temperature just above the MS temperature. And we are holding it here so that the entire steel will be at a temperature of the salt bath right now. Then we are doing cooling it in the air, right? Cooling it in the air so that it will become below MF temperature. Now the martensite will form. So this is the difference you can able to see. It is okay. Anything else? Anything else you can able to see? Look at this part from here to here, from here to here, and just from here to here. What is the difference? Just look at this. Here, this is a single line. Yes or no? This cooling curve is a single line right now. It is okay. What about this? From this point to this point, below MF. This is a single line or two line? What you can able to see here? You can able to see here we have two lines here, right? Two different cooling curves. One cooling curve for the center, one cooling curve for the surface below MF up to MF. But here above MS we have a single cooling curve right now to the below MF. We have a single cooling curve, right, for the surface as well as for the center. But here we have two cooling curves. So that means there is a temperature gradient will exist here. But you can consider there is a very minimum temperature gradient will exist. Temperature gradient means you understand what is the meaning of temperature gradient? Means there is a difference in temperature will be there from the surface to the core. The surface will cool at a faster rate, but the core will not cool at a faster rate. So that's why there is a temperature gradient will exist. That leads to the what? Your residual stresses again. So here the sample will be having residual stress, lot of residual stresses, but the sample will be having very minimum residual stress. I think you people have understood right now the difference between the conventional heat treatment and Martempering. It is okay, or I will explain it again if you want. Shall I move on? Apurva Das, you are there? Apurva Das. Apurva Das. Okay, Swapnamai.
Yes, sir.
Swapnamai, can you differentiate this one with this one? What is the basic difference you can able to see?
Yes, sir.
Okay, let Swapnamai to answer. What is the difference we can able to see?
I had some network issues, sir.
No, sir.
Okay. Okay, Susri Snehansi Pradhan, can you explain this one? What is the difference among this?
Um,
Okay, Saloni, can you answer this one? Saloni Agarwal.
Yes, sir.
Yes. Can you differentiate this conventional heat treatment and this Martempering special heat treatment? What is the difference here?
Sir, in this there is a single line and there is double line.
Single line from where to where? Yes.
Sir, I don't know.
Okay, Tushar. Tushar, can you explain this one? Tushar?
Yes, sir.
Yeah, can you differentiate this one? Martempering heat treatment with conventional heat treatment, that is hardening and tempering.
No, sir.
Okay. Sanjeev Kumar.
Yes, sir.
Yes, can you differentiate this one?
No, sir.
Okay, Samrat. Samrat.
Sorry, sir, I don't know.
Okay, Rameshwari. Rameshwari can explain. Yes.
Sir, in conventional route, in case of we do quenching the steel from austenite below the MS temperature, but in Martempering, quenching the steel from austenite to just above the MS temperature.
Very good.
And in Martempering, temperature gradient will be exist, but in conventional route, no temperature gradient will exist.
Second one is wrong. Temperature gradient will exist here or here.
Sir, conventional route temperature gradient.
Yes, in conventional route there is a temperature gradient.
Yes, sir.
Why there is a temperature? Because these are two cooling curves. Huh?
Yes,
one
sir.
cooling curve is for the steel surface, and the
Another
cooling curve is
for
for the steel center. The same piece of steel, but there is a difference in temperature is there from one point to another point, right? So obviously there will be some thermal stresses will be there. So some residual stresses will be there in the steels, right? Okay, very good. Now, next heat treatment is called austempering. Austempering is this another special heat treatment. The main purpose of austempering is to get benaitic microstructure. And you people remember the benaitic microstructure is the most important microstructure we have in steels because it is tougher, harder, stronger, wear resistance. Many properties are there. If you are talking about lower benite, lower benite is very good as compared to that of this tempered martensite also. It has high strength, high wear resistance, high toughness, high ductility also, right? It is very good and high this fatigue strength also, right? Impact strength also, right? So austempering, what is the heat treatment cycle? You can see we have to take the steel. This is again a TTD curve. This portion. This is again a TTD curve, and this is the cooling curves for the same piece of steel. But we have two different cooling curves. This one is for your center, and this one is for surface. So you understand we have to take the steel to the austenitizing temperature here. Then we are then quenching the steel to a temperature which is at the benaitic transformation temperature. That is basically 200 to 400 degrees centigrade in between them. But basically we prefer to keep the steel just above MS, which is the lower benaitic temperature. Then we have to hold the steel for sufficient interval of time at this temperature. So what will happen? The transformation will take place. This zigzag is nothing but the transformation. The austenite will transform into benite. The moment all the austenite will become benite, then we have to cool the steel to the room temperature again. So this is the cooling cycle after the transformation is complete. So again, I am saying we have to take the steel to the austenitizing temperature, and we have to hold it. After all the steel will become austenite, we have to quench it, but the quenching will be done to a temperature just above the MS. That means at the benitic temperature region, and we have to hold the steel for sufficient interval of time so that all the austenite will become benite. So after that, when all the austenite become benite, then we have to cool the steel to the room temperature slowly or depending upon the requirement, right? To room temperature. So this is called austempering. So austempering leads to formation of benite, but martempering leads to formation of martensite here, right? So this is the same plot you can able to see. Austenitizing region, quenching and holding the steel at this temperature, which is the benitic transformation temperature, lower benitic transformation temperature. The benitic austenite transform into benite at this region. Finally, when all the austenite become benite, then we have to cool the steel to the room temperature. Now suppose there is some data here. This may not be exact data, but still it is a very good data we have to compare the water quenched and tempered steel, mud tempered steel, and austempered steel. The properties. The properties of austempered steel. What is the property of the mud tempered steel? What is the property of water quenched and tempered steel? So this is the hardness value showing. This is impact test value, and this is the elongation value. Can you people figure it out what is happening and what is the difference from this data? Can you people figure it out? Okay, can you people tell me? Okay, let me ask. Okay, if Sita Mishra, can you tell me what is the microstructure in the steel if this is the heat treatment?
So which is the heat treatment? Oh,
This one. The starting phase is the austenite phase, and this is the heat treatment you are giving. So what is the microstructure you will get at the end of the heat treatment? Water quenched and tempered. Can you answer it yes or no? Just tell me. The starting phase is the austenite phase. Then you are doing water quenching and tempered. So what is the microstructure you will get? Okay, Gyanananda, can you answer this one? Gyanananda?
No, sir.
Okay, no, sir. Apurva Das?
Yes, sir.
What is the microstructure you will get after this heat treatment?
No idea, sir.
Okay. Abhay Patra?
Yes, sir.
Tell me the answer.
Chonani, sir.
Abhishek Mohanty?
Yes, sir.
Don't tell me yes, sir. Tell me the answer.
Sir, ferritic transformation.
Can you justify how ferritic transformation?
Sir, no, sir.
How you can able to say ferrite? Can you justify that? What is the weight percentage of carbon in steel? Okay, Abhishek Mahanti, can you tell me at up to what weight percent we will get only ferrite? If you are doing
Sir, 4.3.
4.3. Have you ever seen iron carbon phase diagram?
Yes, sir.
4 point up to 4.3 weight percentage you
Sir,
will get
sorry,
ferrite.
sir. Sir, 6.7.
6.7 you will get ferrite. Are you lateral entry, Abhishek Mahanti?
No, sir.
Okay, fine. You are there when I was teaching IPM subject.
Yes, sir.
How much percentage you have got in IPM? What is your CGPA? Or how much CGPA right now you have?
Sir, 8.3.
You have 8.3 CGPA, but you don't know up to what weight percentage of carbon you will get ferrite.
Sir, right now I don't remember.
Right now you cannot recall how it is possible. Okay, I will stop here. I will not teach anything else. Let me show you iron carbon phase diagram. Let me see how many of you can answer. Okay, I will stop the recording here at least.